In the meantime, I got fascinated with that other thing that Matt was talking about. I just have to tell you, okay, this is just a little side lane. Here was the problem. We were trying to prove Stirling's formula. Tuesday was one of the problems.
I've actually seen this proof before.
Well, here, this will keep Dave occupied here. Here's the problem that came up in class. What is the minimum n so that n factorial has 2009 least significant zeros? So it's a gigantic number with 2009 rightmost zeros. And I think Matt and I have verified that it's 80-50. I'll let Dave figure that one out. You can check it too, because we were going to send it in.
Yeah, some number times 10 to the 2000. You can get all those zeros.
Well,
You would have to have the factorial.
5.
2 and 5.
2 and 5. And you have a 2 on every
I'm
other one.
not saying that n is itself going to be a factorial.
This is the equation you have to solve. Yeah, because here's one. The next one is 15,625, and in 10,000, if 10,000 factorial has more zeros than you need, you know, it at least has 2,000 zeros, and then this thing is divisible by 25s all over the place. So you never have to go past this. You will find if you try to do this that there is no solution. There's a solution for this and a solution for that. So you have to go with this one. That's the
2009 is fine.
No, it just doesn't have, these floor functions don't evaluate out to 2009. It's weird how it kind of jerks along, you know, it suddenly jumps. Like you can't increase this just by 1 because it'll take some of these others with it. Anyway, sorry, that was a loose end. But he triggered an interesting problem, so okay.
Did you see the last email I sent you?
No, what'd you say?
It was about like 3 months that I sent you. I found a website that had the proof of Stirling's formula.
Oh, great.
And it had something that was really similar to what you were looking at, and then they had that square root of 2n thing.
Well, the square root of n I can get. It's the square root of 2 pi that I can't get to come out right.
Yeah.
I will make it a quest. Over the weekend, I will solve that problem.
Augustus, the Morgans would Stirling.
I thought Stirling did it based on Wallace's work. That's
Stirling did it later. Augustus Morgan did it.
Oh, no, De Morgan was 19th century. Stirling was 18th century. I'm sure of that.
Really?
Yeah.
I thought Morgan overlapped.
I don't think so. He was fairly recent compared to Wallace and Stirling.
As long as it's in 1700.
I think Stirling was a rough contemporary Euler. De Morgan was much later. Augustus De Morgan was much later. Check the dates. He may have come up with an independent proof.
Stirling is 17, late 17.
Well, it's in our book. What's it say? 1705 to 1790 or
1692 to 1770.
Okay, there you go. Okay, yeah. But Augustus De Morgan was a 19th century guy. Okay. So now, we are back to our book, and we're looking at the integrability condition for a function to be Cauchy integrable. And just what's the definition of Cauchy integrability, just for you guys that have joined us? What's the deal between Cauchy agreement? Which is what do you do? If I have a function here, gee, this feels like calc 2. If I want to integrate f of x from a to b, Cauchy style, so I want the Cauchy integral from a to b of f of x. how do I define that? You remember? I do a partition, right? And then I have this little width dxi. And of course, A is x0, right? And B is xn. So I have n plus 1 division points here, partition points. And I have n intervals. Do these all have to be the same size? No, they don't. Typically, to do sums, we often choose them to be the same size, but they don't have to be. It's not integral to the definition of unintended. If we take a sum, k equals 1 to n, and we evaluate the function at the left side of the elementary rectangle, right? So, for example, the very first rectangle, they have height f of a and width, whatever the first little jump there was, right? So we're always appealing to the left endpoint of the subinterval multiplied by the width of the subinterval, and then we watch what happens as the norm of the particular partition that's in effect is going to 0. Well, what's that mean? We just shrink the size of the max subinterval below epsilon, for all epsilon. That's what it means for the norm of the mesh of the partition to go to 0. If this thing approaches a limit, we say that the Cauchy integral exists and equals the limit. Okay? All right. Now, we're going to be dead unless we can, well, we're going to have to come up with a candidate limit. That's a task. And then we're going to have to show that this business about partitions getting smaller and smaller, it doesn't matter what partition we take as long as it gets smaller and smaller. So we can have two totally different partitions. As long as the norm of each of them approaches 0, we should be coming up with the same limit. So we don't have a lot to work with here. We don't have the limit. We don't have the limit, and we don't know the dependency of this process on the particular partitions. So what I'd like to do is spend our time to sorry, I had a little flashback there. I'd like to see if we can work that out today. Why the definition of the Cauchy integral is independent of the partitions taken, and how you pluck this lambda out of thin air. Cauchy, when he worked this out the first time, did not have all the tools available to do the proof that we're going to do. So his proof, where he had the technical support, it's correct, but there were some aspects to it that were intuitive for him, and he sort of winked it. And this is the crux of the issue. Notice this is point number 1 under the author's proof of the Cauchy integrability criterion. What's it say? That a continuous function on a closed interval is uniformly continuous. We need that. We need, badly, if f is continuous on the closed interval AB, then if f is continuous on the closed interval AB, then f is uniformly continuous on AB. All right, let's revisit the definitions of continuity and uniform continuity. What's continuity? A function is continuous at a point x0. These are all real functions. A function is continuous at the point x0 if what three things happen? The function is defined at x0. The function approaches a limit as x approaches x0, and those two things are equal. If any of those things go wrong, the function is said to be discontinuous. Is every discontinuity a jump discontinuity? No. What's an example of a function that has a discontinuity at 0 that is not a jump discontinuity. How about 1 over x? Right?
Jumping from negative to positive.
Yeah, that doesn't count. Doesn't count.
I was thinking more like x time. Well, I was thinking trying to